Okay, so thank you everyone for coming back for more non-smooth Hodge theory. So let's just let me just recall where we ended at last time. So remember we had this pi I, which was equal to gamma plus gamma star I, where I was an inner product. So for I equals 1, 2, they were inner products which had comparable norms to each other. And what we really want to assert is that the kernel of pi 2 is isomorphic to the kernel of pi 1, right? Because that's really what we want to do with pi I being the kernel of the Hodge-Dirac operator arising with respect to two inner products. So before we, get stuck into it, I just want to sort of think about how we might do this. So let me just kind of give you a lemma. It's an important lemma. And again, I'm gonna just give you this in a Banach space to really emphasize the fact that actually we don't need a Hilbert space structure here. So let X be a Banach space, and we let X equals, well, okay, I'll put this on the next line to emphasize. So X decomposes in two ways: A plus B and also A prime plus B. Okay, so I don't know, you can think of the picture in finite dimensions. This would be like if this was, say, B, maybe this is A and this is A prime. Okay, so this is maybe what it's like. Then the claim is that the projection to A prime along B, right? So remember that this is the range of the projector, this is the kernel of the projector, restricted to A, which takes me from A to, well, I'm writing A tilde instead of prime. Why am I doing that? So A prime. So this takes me from A to A prime is Banach space isomorphism. Okay, so a homeomorphism. So it's bounded with bounded inverse. Okay, so let's prove this because this is somehow the key to unlocking the mystery. So to prove this, so note that first of all, we have an algebraic condition here. So we need to show that this map PAB restricted to A to A prime is a bijection, right? So we need to prove that. But already proving that it is a surjection tells us that it is an open map because of the open mapping theorem. Okay, so if we now improve that to an injection, then it tells us that the inverse is actually bounded. So from something algebraic, we actually get a continuity result for free. So why is it surjective? So let me show you why it's surjective. So let now A prime be in this A prime, little a prime, and let's decompose this according to this first decomposition into A plus B. Okay, so this is into A plus B. So now let me just act on this with the projection. Okay, so I have A prime is equal to P A prime of B because A prime is already in the range of A. um, well, A prime, which is P A prime A, B A plus P A prime B of B, but this is in the kernel, so this is 0, right? So we get that this is just P A B of A. So that shows that for everything in the A prime, there is something in A, namely this A, along which we have this decomposition. And so it makes this map a surjection, and already, as I said before, this tells us that P A B restricted to A is an open map. Okay, and injectivity then settles it, because an injective open map is a homeomorphism. Well, the inverse is bounded, and together with bijectivity, it's a homeomorphism. So injectivity is easy. So it's a linear map. So A prime B x equals to 0 implies then. So we want to take let x be in A, and suppose that P A prime B x is 0, but if so that's saying that this is in the kernel of this map, of this projector, which means that x is in B. So that means that x is in A intersect B, which is 0, because again we have this decomposition. So this is a very, very simple lemma. Okay, you don't need to really suffer in any shape or form to really get to here. So how does this help us? So how does this help us? Well, remember we have h equals the kernel of pi 1 because we have a self-adjoint operator, right? We've shown that the pi I, with respect to the ith inner product, which is comparable, but with respect to the ith inner product, is a self-adjoint operator, so it'll break up into this, and we also have it for the second operator, right? I mean, we've just changed inner product. So we saw this last time. So if with some miracle, so if we can show, so can we show that h is equal to the kernel of pi 2 plus the range of pi 1 closure? Okay? So if we can show this, then applying this lemma gives us what we want, because we have a common subspace here. We have a common subspace, the range, and we have a kernel of pi 1 and the kernel of pi 2 here. So if we were able to prove this, immediately from the lemma, we're going to have that the projection to the kernel of pi 2 along the range of pi 1 restricted to the kernel of pi 1 will give us an isomorphism, right? And so not only do we get that these spaces are isomorphic, we also get a description of the isomorphism. And often that's really fundamental. You really want to know what the isomorphism is. You don't want to just know that you have an isomorphism, okay? All right. So it seems that I've been a bit naughty here because my screen is it's too big. So it should be there, I think. This changes every time. It's a bit annoying, to be honest. Okay, good. Okay, so we're back to reality. We're back to normal now. So to that end, let me define just h tilde as equal to the kernel of pi 2 plus the range of pi 1 closure. So I'm not claiming that this is a closed subspace or anything like that. This is, of course, just a vector subspace of H. That's all we know, because this is a subspace, this is a subspace. We sum it together. It could very well be that this has a non-trivial intersection. But I'm gonna tell you that that's not the case. So the first thing I want to say is that H is to say, sorry, that the kernel of pi 2 intersect the range of pi 1 is 0. I would like to, if I had time, I would have proven it, but I'm going to leave that as an exercise. It's just a matter of playing around with the Hodge decomposition and these kind of decompositions that we have. If you play around with it enough, it'll pop out. Okay, so I won't prove it, but what this tells us then is that we can write this H as the kernel, at least as a sum where we can put a circle, nice circle around things now. Still not saying that this is a closed subspace. Okay, so just because I've written it in this way doesn't mean that it's closed. But it does tell us that that H tilde is a sum of two subspaces which are mutually complementary. Okay, that's what it tells us. But of course, we want to assert that that this is closed. And ordinarily, maybe if it was a different problem, you would maybe first attack the closeness of this. But actually, we're going to just do it in one stroke and show that this is actually equal to H. Okay. So how do we show that this is equal to H? So I don't know why I've written that really as a lemma. It should probably be a proposition. Proposition. So let me give you a proposition. I'm going to give you a proposition that H is equal to H tilde. Okay? And okay, so let me start with the proof of this. So what we're going to do is we consider the annihilator of this. Okay? And we consider the annihilator of this, so one has to be, so when we first sort of mucked around with this, we did a lot of calculations to try and figure out how to make it really work, and I couldn't make it work by annihilating with the inner product 1. But it turns out that the second inner product gives us what we want, so let me just write down what this is. So this is yx equals 0 for all x in H tilde. Okay, that's what this is. And we show that H tilde perp 2 is 0. So if we do that, we've got everything, right? Already it's a subspace. We annihilate it, we get back 0, which means that this should have been the original space to begin with. Okay. Okay. So, so let y be in this space, right? H tilde perp 2. So let y be in this space. So this is satisfied only if these two conditions are satisfied. That 0 is yu in 2 for all u in the kernel of pi 2, and b 0 equals y v2 for all v in the range of pi 1 closure, because H tilde by definition is equal to kernel of pi 2 plus the range of pi 1 closure. Okay, so we can consider always breaking up something in here into components of these by construction, and then the annihilator of this is equal to each of these two things being annihilated. Okay. So let's see what we get from B. So from B, right, we have that for all v in the range of pi 1 closure, we have 0 equals y v in 2. But remember, the inner product in 2 we can rewrite now with respect to this b. Okay, so this becomes BYV in 1. Okay? So that means that BY, okay, BY is actually in the range of pi 1 closure perp with respect to inner product 1. But that is precisely equal to the kernel of pi 1. Okay? Good. And if I'm just to recall that, this is the kernel of gamma intersect the kernel of gamma star 1. Okay, that's what we have. A then gives us that for all u in the kernel of pi 2, 0 is equal to y u2. But that means that actually that y is in the range of pi 2 closure, because this is saying that it's in the orthogonal complement of the kernel of pi 2. Okay, that's what it's saying. So, and this is equal to the kernel of pi 2 perp with respect to the second inner product. Okay. Now, so recall now. So recall. That this range of pi 2 closure we can write down as the range, and this is Hodge, coupled with that transformation rule that we established, range of gamma star 1 closure. Okay, so this is what we have. So this tells us that y is going to be equal to some x in the closure of the range plus b inverse some w. So there exists an x in the range of gamma and w in the range of this fella. Good. Now, let's just multiply everything by b. So we have b, which is equal to bx plus w. Now, what is what is by? So y is coming from y is what did we say? So we had here that by is in the range of pi 1. Okay? It's in the range of pi 1 and in the kernel of these operators here, and from also the construction we have, let me just see what's going on. So y is in the kernel of this. So let me see here. So we should have an argument here by nilpotency. So what am I missing? Sorry, this is sorry, yes. So so w is in the range of this gamma star of 1, and x is in the range of this gamma. So just let me gather my thoughts for a second here. So why am I doing this? So certainly this is in the so this is in the range of this. I want to conclude that by is in Okay, so this is certainly in the kernel of so this is also in the kernel of gamma star 1. Okay, so that's certainly true. Where's the condition on by? So by v1. So this tells us that this is in it's not in the range. Aha. So by from this calculation tells us that it's in the kernel of gamma star 1. Okay, so that's what we can conclude. So what we conclude from this, so this from this, sorry, this is where I was missing this step. So from B we have that this is in the kernel of gamma star 1. In fact, it's in the intersection, right? It's in the intersection of the kernel of gamma and the kernel of gamma star 1. So that's good. So that tells us that Bx now is in the kernel of gamma star 1. Because I can just write, since Bx is equal to By minus W. Okay, so vector spaces. Okay. So that tells me that x is in the kernel of gamma star 1b, and my x was in the range of this gamma, right? Intersect the range of gamma closure, because that was the choice that I had for this. But this is now, so what is this? This kernel is actually the kernel of gamma star 2. And so this is equal to 0 since h is equal to, if we now consider the operator, if we consider this operator and take its adjoint, we get that this is equal to kernel of this plus the range of gamma closure. Okay, so with respect to the into the second inner product. Okay, so this is what we get. So that's good. So it tells us that actually this x term is 0. Okay, so you can see that this stuff is a bit tricky because it, regardless of how many times I've done it, it still confuses me a bit. So now y is equal to b inverse of w. That means that w is equal to by, which is in the kernel of pi 1, right? That's what we had from this condition, from condition B again. So this is in the kernel of pi 1, and so what is the condition on by? And it is in so it's in the kernel of pi 1 and the range of where is it? It's in the range. So where did we start off? So we started off with where's the? So we're in the kernel here, and W is in this range, so that's in the range. So that means that that's so this is the W, so it's in the range of pi. So W is in the range of gamma star 1. Okay. But this is now contained in the, so remember the kernel of pi 1 is the intersection of the kernel of gamma and the gamma star. So this is kernel of gamma intersect the range of gamma star 1 closure, which is 0. Again, because h is equal to the kernel of this plus the range of gamma star 1 closure with respect to inner product 1. Okay? So that tells me that w equals 0, which means that y equals 0, i.e. h tilde with respect to 2 is 0, and that tells us that h is equal to h tilde. Okay, sorry, bit of a struggle. Working out where things land is a bit difficult. But with this, I want to give you an abstract. So I want to give you now the first theorem. So this is an abstract Hodge type theorem. So we have that the kernel of pi 2 under, of course, these conditions is isomorphic to the kernel of pi 1 as B spaces. So the bounded iso with iso phi, which maps the kernel of pi 2 to the kernel of pi 1 given by the projection phi equals to the projection of the kernel of pi 2 along the range of pi 1 closure, restricted now to the kernel of pi, sorry, I need to go the other way with this, pi 1 and pi 2, kernel of pi, so this takes me from the kernel of pi 1 to the kernel of pi 2. Okay, and the isomorphism the inverse can also be written in a nice way. So this is the first abstract Hodge theorem that follows directly from this. So now let's get back to reality. So back to reality. Let's take a step down from some of these abstract stuff. So M compact, smooth with empty boundary as we had before. We have G, which is a rough Riemannian metric. And we saw before, so last time, if G infinity is a smooth metric, smooth Riemannian metric, then there exists a C greater than or equal to 1 such that G is comparable to here with this constant C, right? So their norms are comparable above and below. With respect to this, we have that the closure of D with respect to G is the same as the closure of D with respect to the G infinity. And we have that the kernel of DG now, right? So with the rough Riemannian metric, via this theorem is isomorphic to the kernel of DG infinity. But of course, this from the classical Hodge theorem is now isomorphic to the singular cohomology on M. Okay? So in the remaining time, I want to say, okay, well, what happened to considering the kernel of DG restricted to K forms? Okay, that's really what we want to get to. If we want to get to Betti numbers, that's where we need to go. So okay, so I want to say something about splittings. In fact, I want to say that this Hodge theorem, we could have argued it with, if we wanted to just stop here, we didn't actually need to know anything about these operators. It's enough to consider a cohomology that you create with in a Hilbert space sense with respect to the operators gamma and gamma star, and you can immediately reason from it if you didn't care about the projector and if you wanted a very cheap, dirty theorem that gets you here. So you don't actually even need to know that these operators pi I self-adjoint operators with respect to the ith inner product or anything like that. In some sense, the reason that we really do all of this hard work, well, firstly, it's interesting to know this about the operators. If you want to use operator methods, you want to know the spectral theory of the operator. But the bottom line is you want to also get to splittings. Okay. So for that purpose, let me maybe talk about splittings now. So let me tell you. Let's take some operator with domain. Okay, so I just want to phrase this abstractly. And let's suppose that H splits into H0 plus H1. And that this projector along this splitting commutes with this operator on its domain. Then the claim is that the domain of this operator restricted to Hi is actually equal to the domain of well, this is trivial. There's nothing here. I'm sorry. I don't know why I'm writing this. There's nothing here. So this is the first consequence, which is easy. The second consequence is that is more important, and it's that the range of this Hi is actually equal to the range of the operator intersect Hi. And then the third thing is the kernel, right? So the domain, so one of course implies 3, is that the kernel of this thing Hi is equal to, so this is really the non-trivial statement. The kernel of this intersect Hi. Okay, I'm gonna leave this as an exercise because the proof is relatively simple. But where do we go with all of this? So the bottom line is this, right? So I want to first define something which many people call the Macintosh modulus, because this works more generally in for operators beyond just the self-adjoint ones. In this case, this disagrees. So this is pi signum pi. So signum is the so signum of x is just the characteristic function from 0 to better be from 0 to infinity of x minus the characteristic function from minus infinity to 0. Maybe I'll call it t. Okay, so these are self-adjoint operators, and I don't want to get stuck into it because this requires some functional analysis which involves the spectral theorem and so on and so forth, or whichever way you want to really argue it. But with this, what one can do is to reason as follows, right? So I'll give you a proof sketch of this. So for all alpha positive, the kernel, so these operators will have a fractional power alpha. The kernel of the alpha power will be equal to the kernel of pi, and the closure of the range of the alphath power will be equal to the closure of the range of the original operator pi. Okay? So a proof sketch of this would be to use functional calculus to describe this operator. So functional calculus is a universality theorem that tells you that if you have some, that axiomatically characterizes functional calculus, and if you have one way of computing it, basically you have, all ways of computing are the same. So what I'm going to look at is this operator f alpha of pi, where f alpha of t as a function is the modulus of t to the alpha 1 plus t to the 2k. So this operator will be a bounded operator, and then we'll multiply it by this other operator so that we get all the domains and so on and so forth, right? And using this and using functional calculus, one obtains a conclusion, right? Conclusion via functional calculus. So I won't get into it. It's It's not super difficult to do, but I just want to kind of showcase this to you because I want to sort of say where we're going to go with that, right? So the bottom line is that we had kernels and ranges of operators, and now we want to replace them with fractional powers because what we want to know is the following. So proposition, suppose that h equals h0 plus h1 as we had before, and there exists an alpha positive such that p h0 h1 and this to a power of alpha is equal to 0, then we can conclude that the kernel of the original operator intersect hi, which is, of course, by the previous theorem, the kernel of the alphath power intersect hi, and we have that the range of this pi closure intersect hi equals the range of the alphath power of this operator intersect hi. And of course, this is again, let me give you a proof sketch of this. So the idea, so it's clear that if we take these spaces, if I take kernel of pi intersect hi plus the range closure intersect hi, that this is in h. So what you really want to do is to start with a u in h, decompose it as u plus w in the kernel of pi, kernel of, so as we wrote before, kernel plus closure of the range. But then you can substitute this for the kernel of pi to the alpha plus the range closure of alpha. And once you do this, you use the fact that you've got this commutator with the projector to show that actually the projection, sorry, I've written u, this is v. You can show that the projection along this splitting of v and w still keeps it within these spaces, and the ranges are in h0 and h1 respectively. Okay, so that's the way that you reason it. So you show that p of hi, and I'll call this hi tilde for the other one, of v is in the kernel of pi alpha, and similarly p hi prime of w is in the range of pi alpha. Okay, and so the lemma from before will then give you the necessary result. So this is good. This then leads us to where we want to go, which is abstract Hodge along a splitting. So as before, we have h equals to h0 plus h1, and we have gamma, pi I. So we have two inner products now. So this is going to be gamma plus gamma star I with respect to inner product I as before. And suppose there exists an alpha such that p of h0 h1 of this ith. So now we need it for both operators. This is 0. Then we have that hi is equal to the kernel of pi 1 intersect hi plus the range closure of pi 1 intersect hi, which is equal to the kernel of pi 2 intersect hi plus, again, the same range as pi I intersect hi, which tells us that the kernel, it's gone dead. Let me just revitalize my pen. I don't know why it keeps doing that. The kernel of pi 1 intersect hi is isomorphic to the kernel of pi 2 intersect hi. Okay? So immediately, right, this gives us what we want in terms of the splitting. So if we go back, so now we're going to more or less permanently go back to reality. So back to reality. So we have L2 of forms splits. I mean, this is now, you can do it by induction argument, k equals 0 to n of L2 of the k forms of M. And we have this projection. So this is often why people really studied, I guess, the second order operator, because what we have is actually the second order operator and pk commute, right? Because what is the second order operator? So the second order operator is dg squared, which is d star g plus, well, maybe closures here, d star g d tilde. So of course this maps k forms to k plus 1 forms, and this maps k plus 1 forms back to k forms. So this is how you see this projection. So again, factoring through the original theorem, if we now have G, which is a rough Riemannian metric, G smooth, any smooth Riemannian metric, and M is compact without boundary, then that tells us that the kernel of dg restricted to k forms is isomorphic to the kernel of dg infinity restricted to k forms, which is obviously isomorphic to the kth singular cohomology of M. So so that gives us the thing that we promised. Good. Now, last time there was a bit of a question and a conversation. So here I've given you the specific results here for the compact boundaryless case. But what I want to really now talk about is the non-compact situation. Okay, so what this allows us to do is really to address the non-compact situation. So, okay. So the first thing is that let's suppose that we have H, which is a smooth metric. Okay? But incomplete. The problem is that I can now think of the domain of two operators that I build with this, right? So the domain of this is U in the smooth intersect L2 forms, such that du is in, so this is with respect to H, right? Du, I should, okay, before I write this, I really want to maybe emphasize, oh crap, maybe I want to really emphasize here that, so from here on, M non-compact. Of course it can be compact, but M can be. Okay, it makes sense. It's non-trivial if it is non-compact. So let's have a look at this domain, and I'm going to look at another domain, which is this is DCC, which is just the compactly supported functions, the closure of the complex. The domain is just the smooth compactly supported sections. In this case, even in the smooth situation, DDD closure will generally be much larger. So the domain of the closure will be larger than DCC closure. Okay? So that's something to keep in mind. And if M was chosen to be a manifold so if M was the interior of N, where N is a manifold with boundary, so we have, this is N, this is n, and m is the interior here, then these correspond, so this would correspond to the relative, well, yeah. So these two correspond to relative and absolute cohomology. So already we see this. Okay, in the smooth situation, even something we have quite non-trivial. But I wanna first start you with a lemma here. I know we have a bit of a race against time because I do want to tell you some things. So the first thing I want to say is that if we define, so if G was a rough metric, and D, DD, DCC defined as, let me just copy and paste this in the interest of time, if I can find it. Just use my mouse. It's easier for me to find it then. So let me just define this and change the, oh, it didn't work. How do I copy? Copy. Okay. Paste this. Okay, so let me change this to a G here. Oops. A G, and this also to a G. Okay, if we define these two, then D2, which is defined as the closure of this, so this exists, closure which is defined to be D0, right? And so I'm going to again give you a proof sketch here. So the proof sketch is that you exploit the fact that d of m, the exterior derivative commutes with pullbacks, and you cover everything by locally comparable charts to deduce that if un converges to 0 and dun converges to v, then that means that v is 0. Okay, because you can cover by these charts, you can pull into Rn, and then you can, as long as you hit it with a compactly supported section or compactly supported function and so on and so forth, nicely localize things, then the bottom line is that you will essentially have something going to 0, a form that can be extended out on Rn that goes to 0, and from the fact that on Rn you have a unique closure, you can deduce that v is 0, right? And then it's pointwise 0 everywhere, so it's 0. And you do this for, so this is for un in dom dd, but if it works for the larger domain, it's going to work for the smaller domain. Okay? The more interesting thing here, I think, that I want to really point out, so what's important here, remember, in all the abstract theory, we really needed the operators to be nilpotent. So the bottom line is that this and this are nilpotent. Okay? So how would we prove that? So let's do it for the D2. So let U be in the range of D2. So remember, it's enough to show it for the range of D2 because then it's already going to be valid for the closure. So that means that, okay, so if we're in the range by the density of the domain, so this is a dense operator, we have a UN in DOM DDD such that UN converges to U, and yeah, let me say DU is in the range of, and then DUN converges to DU. Okay, this is what we have. But okay, so let Vn be equal to DUN. Okay, so UN, remember, if it's in this domain contains smooth objects. They're L2 and smooth. So, so this is going to be again in DOM DDD because it's again the exterior derivative acting on a smooth thing is again smooth. Why? So why is it in? Okay, so I shouldn't say that straight away. I should say okay. So the condition here is that du has to be in L2. But what's dvn? Dvn is d squared un, which is 0. So that just comes from the fact that the exterior derivative on smooth functions is a nilpotent object. So that means that Vn is in the DOM DDD. So now we have something here. We have Vn converging to V, and we have dVn, which is identically 0, which means that V must be in DOM D2, the closure, and dV is equal to, or whatever it's equal to on this here, which is 0, right? So that means that the range of D2 is contained in the kernel of D2. And of course, because it's a closed operator, the range closure is now contained in the kernel of D2. Okay, so that's the proof. So similarly for D0. So these two extreme ends, and this is a non-compact manifold, we don't assume any completeness or anything. This is with respect to a rough Riemannian metric. We always are guaranteed that these extensions are actually nilpotent extensions. Now, I want to just remark that if we now have DE, D2, okay, so this means containment as domains, and this is nilpotent, this is closed extension. It does not follow, right, that DE is nilpotent. Okay, so just because you have a closed extension sandwiched in between two nilpotent extensions doesn't guarantee that it is nilpotent. So let me give you a quick example in the remaining minutes. So let's take this to be the Euclidean ball, right? So the Euclidean ball, closed ball, and I'm now going to choose this to be the closure of an operator which I'll call DE infinity with domain DE infinity equals U in L2, or smooth, I should say, smooth on the ball, with d theta cut U restricted to the boundary 0. Okay, so this is the ball. I'm now computing this in radial coordinates, so these are spherical coordinates, and the theta is a parameter in here, right? So theta and theta and phi are on the boundary, so on S2. This is on S2, and then we have the radial coordinate R here. So R, theta, and phi are spherical coordinates. So the way that you can argue this is we can look at a one form. So let's look at a one form, a smooth one form. So F will be equal to something like FR dr plus F theta d theta plus F phi d phi, right? That's what this one form would look like. And if this is further if F is in the domain of DE infinity, this happens only if and only if 0 is d theta cut this F restricted to the boundary B, B is 0, and that's the same thing as F theta evaluated at 1 being 0. Okay? So we'll just set actually f theta identically equal to 0. We'll also set fr identically equal to 0. So for reasons you'll see in a minute. So now my f under all of this is just an f phi d phi. And if I compute df of this, that's going to give me dr f phi d wedge d phi plus d theta f phi d theta wedge d phi. Okay, so I'm going to just assume that this, so I want to just assume now that f phi of r theta and phi is just a function of theta. Okay, so this derivative then gets killed. So let's compute df. So what we want is, if it's nilpotent, then the second power has to be, then the df has to be in the domain of the original operator. So let's look at, so if df is in the kernel of de, then it means that df must be in the domain of de. Okay? So let's have a look at 0 of d theta cut df restricted to the ball. So that's going to simply be, so this is just the partial derivative now. This term is 0, it's just the partial derivative hitting this thing. So that's going to give me a prime of theta d phi. Okay, that's what I get. So if it's 0, then that means that, so that means that I have to conclude that a phi of 0 theta is equal to 0. So I can set a equals to 1 in this instance. Okay, I set a equals to 1, so certainly the derivative is not 0, and that gives me that df is not in the domain of this de, because it violates this condition. Okay, hang on, I don't want a prime, sorry, I want I want a prime equals to a constant, right? So I want, well, I can choose any function. Choose any function such that a prime is not equal to 0 on the ball. Okay, choose any function you like. That gives me then that df cannot be in the domain of this de, which means that df is certainly not in the kernel of this de by taking the contrapositive. Okay, so that shows you that actually, in fact, this example really highlights that considerations about nilpotency is going to arise from some information that you might have at infinity, at a boundary, at some singular set that you've maybe removed, and so on and so forth. That's why I really wanted to give you this example to just highlight how possibly boundary conditions affect nilpotency. Okay, so I'll draw that all out in a second, but I just want to give you now a last sort of theorem in all of this. So let me write down a theorem. Okay, so maybe this is where we kind of end. So let G1 and G2 be rough Riemannian metrics on M, possibly, well, I'll put this in brackets, possibly non-compact, possibly, possibly non-compact, possibly with boundary. Okay, I don't care. And suppose that these two metrics are comparable. Suppose there exists a C greater than or equal to 1, so that these metrics are comparable almost everywhere. So bounded above and below. And let DE be a closed closed. Well, it'll all already automatically be densely defined if I say it's an extension of this D0. Extension of D0, i.e. D0 is contained in DE, and nilpotent. Okay, that's critical. Define DEGI equal to DE plus DE star GI. Okay, so this is now well defined. So with respect to GI, right? So this is now well defined as an operator from all of our abstract theory. Then we have that the kernel of DEG1 restricted to K-forms is isomorphic to the kernel of DEG2 with respect to K-forms. And what is this isomorphism? So this is for all K between 0 and N so the isomorphism is described, so the projection to the kernel of DEG1 plus the range, along the range of DEG2 closure restricted now to the kernel of DEG2 intersect with L2 of the forms. Okay, so that's what I really want to kind of tell you. This more or less brings us to the end of the mini course, but let me ramble on a little bit more if I can entertain you. So I just want to really tear this apart a little bit. So when we talk about something like this, right? DE plus D star GIE. So I just want to really say that if there is boundary or singular information, so possibly topological singular information, so possibly topological singular info at some boundary, that's where the nilpotency is really going to come in. Okay, that's going to influence that. This thing, of course, contains the topology of the interior. Okay, so I'm not saying that this is gospel. I'm just saying that this is sort of the broad picture of what's going on. Okay, so it's to kind of make sense of all of this stuff. It's really this object here that contains the geometry. So what we really sort of said here, the fact that we have a theorem of this sort, that if we change this geometry in a way that keeps the topology intact in some sense, what this is really saying is that the operators still see the same singular information. The singular information, of course, can be influenced by whatever's on the interior. That's, in some sense, what we want to measure. But maybe there's some contributions coming from a boundary or some other singularity that you've sort of thought about, that you've tried to encode into here, okay? And we want to add this geometry so that it becomes easier to compute. If we just deal with this object, this is not a self-adjoint operator, this doesn't have a good spectral theory, it maps, you know, K-forms to K-forms, but it's not very satisfactory the way that this operates, right? So we can sum these two things together, and maybe this is not the best combination. Maybe you want to have, remember, we can also look at fractional powers of this and we get interesting information. So maybe you want to take different combinations for a problem that you possibly have to encode the kind of structures and information you need in order to really compute information about an operator that is a geometric operator which carries the topological information, okay? Think of it almost as something like an infinite dimensional coordinate system somehow. Maybe you want to choose an optimal geometry that allows you to somehow compute these things in the most, interesting or the easy way possible. So I've been talking about kind of singularities, and I've been talking about all of these kind of things. So how might this actually really evolve? So, or how might this come about? So a very concrete picture. So maybe you want to take Ricci flow. Okay, so suppose now you have GT for on extinction time. Okay, so T is the extinction time on your flow on M. So M closed. Okay, it doesn't need to be closed, but okay, suppose you have that. So instead, let's lift this problem. Well, actually, let me not call that M. Let me call that sigma. Let me define M now to be sigma, 0T cross sigma. And now I'm going to look at a metric H. Of course, this is all smooth, but you'll see where this information comes in. So this is going to be dt squared plus gt. Okay, so what we have is, well, sigma, and then we have it possibly deteriorating to something at t. This is at 0. Okay, maybe it's shrinking. I don't know. It's doing something, and of course, on this manifold, MH, which is now an open manifold, we have DH. So is it maybe possible to try and use, so the extensions of these operator, you know, it's very likely that the extensions can see all the way out to what happens at the limit, because the extensions are in some sense a closure. So, you know, can you maybe build an extension? Can you build, you know, DE such that info on the circle region can be computed via DEH? Or maybe not, maybe DEH is not the right metric. Maybe you don't want to use the metric coming from the Ricci flow. Maybe you want to now perturb the GT term in some bounded way to some other metric. I mean, it could be that there is a much more of a nicer metric which somehow encodes the information that you want. As long as it's bounded above and below in this sense, you're good to go, right? Maybe also the point is that the dt squared is not the right thing that you want to choose. I don't know. At this stage, I'm just rambling on, and I'm talking about, you know, potential possibilities. So this is a picture that I looked at with my good friend and colleague Louis Yudovitz. It's something that we want to try and still compute to see. So for instance, in high dimensional and high dimensional Ricci flow, understanding somehow things like the Betty numbers of these spaces seems to be an important problem. So I have to really thank Louis for introducing this to me, because he's the one who kind of told me about this problem. So in fact, some of what we started and some of the work that I started with George Habib, some of it was continuing, but it was somehow really motivated also by trying to get to this picture. But before we got to this picture over here, we wanted to just really understand this picture to make sure that everything holds water when everything is okay. So, I mean, this still contains the power to do the calculations you want to do, because we've given a lot of flexibility in terms of the kind of extensions that you can use, as long as they're nilpotent, building operators, you know, trying to use these operators to compute this information. And also we have this even in the situation where these kernels might be infinite dimensional. We still show that changing the geometry in this kind of L infinity way just keeps these kernels isomorphic. So in some sense, when you have, so one interpretation also is that when you have these metrics GI, which are Raframanian metrics, the bottom line is that the singular information that it sees is purely geometric, because topologically everything is still very stable. This is still somehow a topological quantity. Of course, this can be equated with an L2 cohomology theory, For the operator, you know, DE actually, so maybe it's influenced by the E again, but all of this is still isomorphic to an L2 cohomology, which is purely determined by this nilpotent structure here. So it's really saying that what we have here are geometric singularities, they're not topological singularities, and that also allows us to justify the terminology in my paper with Sajjad and with Mike Munn, where we called it geometric singularities. So here you've got proof that they are really geometric singularities. I know it's a few years late in coming, but you can now somehow justify that terminology because it clearly shows us that somehow the topology, whatever this is measuring, topological information, certainly in the closed case, this is really topological information. We see that it's unaffected by our choice of metric. That's all I have to say. So thank you very much for your attention, and it's been really fun for me to try and think about some of these things, and I hope you are also motivated to maybe think about some of these things. And if you have any ideas, you want to work on anything together, I'm always around. I'm always open to collaboration, so do let me know. And last but not least, I just want to thank you all for your attention and for attending this mini course, and thanks to Sajjad also for organizing it. So I'll shut up now.
So maybe we should keep in touch.
Absolutely. So let me just also say as a closing remark to all of this that I have considered differential forms. I've considered just the case of differential forms on a manifold. But in our paper with George Habib, we actually consider vector bundles, and we consider nilpotent operators on vector bundles. So you could look at far more complicated objects. You can look at, for instance, taking magnetic operators. So this is where you take D and then you add some odd form to it, because that'll still keep it nilpotent, and you'll still get a complex, you still get interesting stuff. So if you're in a non-smooth geometric situation, maybe looking at things like differential forms is not, the traditional differential forms might not be the right object to look at. It might be that you've got some more fundamental, more interesting objects that you can construct out of it, but where you can still exploit nilpotency. So in subelliptic situations, this happens, of course, right? And then the replacement for differential forms are called Raman forms. So already in a subelliptic situation, you have this. So the reason, at least on this mini course, for your benefit, I presented everything as abstractly as I could. I just want to share kind of the abstract picture that I know and partly that I've developed with all of you, because the structures that might pop up in your specific situations that you want to analyze might not be this thing here. And you want somehow to really, the fundamental thing really here is that what's important is not the order of your operator, okay? This operator, it doesn't matter whether this is first order or a billionth order, it doesn't matter, right? What matters actually is just its nilpotency. But other structural features of the operator, the ability to take these combinations, maybe take powers, so that's why I wanted to really show you this lemma that when you take alphath powers of these operators, you get interesting things. You get that the kernels and ranges are the same. So the reason I showed you that is because maybe the first power of the operator is not where you have the right tools to understand regularity of solutions or something that you need to really understand about this operator when you're looking at the kernel. So just as a caveat, please keep that in mind and look for nilpotency to try and prove something structural, so you get a Hodge theorem. But if you need to compute specifics, then those kernels are equal to all powers. And that's why we also need to know that the operators are self-adjoint. You need some sort of spectral theory. If we didn't have that and we tried to argue all of this without that, just by using the Hodge decomposition and not knowing anything about the operators, we won't get that extra information about powers of, you know, the kernel of the powers of the operator being the same as the original kernel, etc. And those things are vital when you want to actually do computations with it. So that's the last thing I want to say and I want to leave you with.